Thank you, Jero. Thank you, Andy, for this introduction. I don't know if my presentation will be at the level. To me, it's a chill meeting. We should all discuss these algorithms. If you have any questions at any point, don't hesitate. It's going to be a presentation that leaves a lot of things open. A lot of things are intentionally vague because I don't want to go too much in details. There are too many things to cover. So yeah, I'm a postdoc at CCM, and I've been, at the beginning of my postdoc here, I had some basic knowledge in deep learning, not a lot, and I know that I wanted to work on problems where the data is so beautiful and so impressive that you know data-driven models are going to have a lot of impact on the problems you tackle. So my presentation is getting started with deep learning for science, very broad. I'm going to tackle only a selection of subjects. So I'm sure you've heard that data-driven models, so deep learning model is what? It's a data-driven model that has a succession of nonlinear layers. I'm sure you know that it's been applied to a variety of scientific domains successfully in the past years. Here I give, for example, protein structure protein structure prediction. This is AlphaFold 2021. In particle physics, you have this jet classification network that is 2022. In weather prediction, you have this model from people at Google which is capable of evolving future states and generate future states of the weather on Earth that has improved predictions a lot. But also in biomedical imaging, in quantum physics, neural networks, deep networks are used to approximate the wave functions of systems of electrons. And in astrophysics for the detection, it's just an example of gravitational waves. So it's a wide range of scientific fields, and I'm not even sure I'm an expert in any of them. I work on machine learning. I'm not going to pretend I'm expert in it. This presentation is more to give you a form of feedback, experience feedback, or an introduction to deep learning for science. You have your scientific problems in mind, you want to tackle them, you have a beautiful data set, and you like to know how to do it. And most importantly, you'd like to know what are the implicit choices that you're going to make, so choices that you're going to make without even realizing it, but that are actually going to influence a lot the outcomes of your deep learning model. So this is what it's about. And in order to not give a boring lesson about this is a transformer, this is a diffusion model, this is this, I'm going to focus and I'm going to have a recurring example that is one project that Jero mentioned, which is solar prediction. It's a project that we've worked on recently, we are still working on, and I'm still working on it a lot, so if you have any questions, don't hesitate. This talk is not a research presentation. I'm not going to give you results that have been validated all the time by empirical studies. I'm sometimes going to give you things that I noticed in practice that was aligned with what other people at the Flatiron noticed in practice. So don't hesitate to debate if you think there is debate. It's not a comprehensive overview, as I told you, and I apologize in advance if some of you are working on certain models that I'm not going to mention. And it's not an implementation guide. For implementation matters, you have Tanya's talk just after. All right, so the way we're going to proceed is I have these different steps that I think are important when you want to build a project in deep learning for tackling your scientific application, scientific problem. And we're going to follow them. And every time I'm going to mention what we did on the sun to then try to give you some principles that are applicable to other projects. So data, training objective, architecture, training, evaluation. That's the agenda. So first of all, the data. What you see here is the sun. It's our nearest star. And you see an observation of the atmosphere of the sun in an extreme ultraviolet measurement. You have these loops that you see here that constitutes one of the most complex dynamics that you can observe from Earth. It's very complicated. This is a very complex system. And here, these loops, basically, they go from the surface of the sun all the way to the atmosphere. I don't know if you saw it, but you also have events that occur. You have these solar flares, these form of explosions that you'd like to understand and that at the moment are very hard to model or to generate. Just so that you realize the complexity of the problem in practice, so that you start realizing it. 1 pixel on this image is the size of Ireland. And you have thousands of pixels. So you can't just run PD simulator after having identified the physics. It's not as easy. So it's a problem that it's across a Flatiron project. I didn't work on it alone, fortunately. I worked on it with people at CCM, with people at CCA, with people outside of Flatiron, with people at NYU, with people at Polymathic. I think it's important to mention that. So it's one example of a problem. There are millions of scientific problems that you can tackle with a data-driven approach. What you have in general is different measurements. Here you see another extreme ultraviolet measurement on the sun. You see here a Dopplergram, which is a measurement of the velocity at the surface of the sun. You also measure the magnetic field. So you have these different measurements. Here, it's a case where the data comes from a telescope. So you have a telescope from Earth. We take this data. It's a remote sensing case. You'll see that it has a lot of implications. As it's often the case, you don't necessarily have control over the data that you want to model. It's really, this project, it's really an example of vertical, where the scientific problem is there. It existed before AI, before even we talked about transformers, and we are tackling it in its full complexity. Any questions so far? So it's just an example of the data of the problem that we're going to tackle.
May I ask a question as an outsider? What is the scientific problem? I mean, the surface of the sun is very big. There's all of these different things. Is one after statistical properties of these events? Is one after, what's the real problem?
Yeah, it's a very good question. So the problem here is to emulate the dynamics. So we want to build an emulator of the dynamics that we can condition so that you predict the conditional distribution of the future given the past. So it's like in weather forecast. It's basically, if people know weather forecast on Earth, it's basically weather forecast, but with the surface and the atmosphere of the sun. And I'm gonna mention and formalize it a bit more later. Any other questions? All right. So general principles. First one is very easy. Of course, select the spatial temporal scales that you want to study in the data. In our case, we wanted to study hourly evolution at the scale of the telescope, or with just a downsampling of a factor 2. This is obvious. I'm not going to talk too much about this point. Second point is important. I don't know if it's clear for people, but in general, the data you get from missions like that are highly under-resolved or highly incomplete. So it's not the case for this project, but in general, you may have data assimilation techniques that helps you basically obtain data which is more characterizing the phenomenon that you're studying. If you look at weather forecasting, for example, weather prediction, you're not going to work on the measurements of the balloons that are on the atmosphere that are very sparse. You're going to work on a reanalyzed data set. And it's not necessarily a choice that you make or not, because of course, if you have more beautiful data available, you're not going to use the sparse data available. But I want to mention it because it's very important in the applications that we hear of. You have this aspect really of, do I have access to a full state of the system? Do I train my model on a full state of the system? Or do I train it on a very sparse observation of the system? We're going to come back on this point later. In the case of the sun, remote sensing, we have access. The data we have is only what we have access to. So most of the time, the data we have is from an Earth observer. So you have access to the surface of the sun, not what's on the far side of the sun, not always. And even on the surface, on what you have access to, if you look at the resolution of your, if you look at the pixels that are going to be close to the edge of the observable disk that you project on an Earth observer, you're not going to have a data that is of as high quality as what you observe in the center. You really have, in that case, a problem, which is that you observe images of a spherical object, basically. So it also reduces even more the data you have access to. And it's really a difficult problem because basically we don't have captors inside the sun. So the data you have is about a process that is 3D. And the only data you have is the 2D projection of the surface and some layers in the atmosphere. So it's really a case where the observations you're trying to model are quite far from actually the entire state of the system. And we found it's important in quite a lot of projects. Pre-processing choices, we know it's important, but we very often underestimate it. Pre-processing choices are going to impact a lot any data-driven approach you have on your data. I'm going to give you a very extreme example. This is actually the raw velocity measurements that you obtain from the sun. And what you see is that you have a blue shift on the left and a right shift on the right. Why? It's because the sun is rotating. So the pixels that you're going to observe here, their velocity, they are coming towards you. So when you measure the velocity, you're going to have a blue shift. And the same goes for the right side of the sun. So if you don't do anything, what you provide your model with is just a map, basically, of the longitude, where your pixel is in terms of longitude, with some details that are the dynamics of these points, but that your model is going to take forever to pick up. But in the end, that's what you want to model. So pre-processing is about giving the model what you want it to model in priority. And here you do a pre-processing, and now you see that these regions, which are actually the ones that we want to model, are way better, are way more visible. And it's not just with human eye; it's also in the data. So I emphasize that because we all make. It's not necessarily a mistake, but we always underestimate the time that we should take on data before building a data-driven model. Any questions so far?
One question. What's the periodicity of the rotation of the sun?
Sorry, can you say it again?
The period of the rotation of the sun.
So it depends on where you are in latitude, but if you are at the equator, it's going to be something around 22 to 23 days.
So you have some periodic structure to your data set.
Yeah. And we can estimate in advance the velocity. That's not a difficult problem. Yes?
Taking the weather forecast analogy, if you train based on clouds over the Atlantic and then try to use the same model on clouds over the Pacific, you'll get bad results because the ocean currents are different. Yeah. Is there anything analogous like that on the sun?
Yeah, unfortunately, and it's even more, I think, because for example, if you train a model only on the center and you don't do any reprojection, your center patches, basically each pixel is going to have the same volume, the same surface behind it. If you go now to the right part of the sun, the pixel that is here, it's actually way bigger than the pixel that was here. So if you don't do anything, you train your model here, then you try to apply it here, it's not going to work. So,
is to like ocean currents, like sort of fixed behavior of different parts of the sun, or?
So I know. So I'm not an expert in solar physics, but we have an expert in solar physics in the team. What she told me is that you have phenomenon like that. For example, depending on the cycle. So you have cycles that are several years long on the sun, and depending on the cycle, if you're at a high cycle, the regions that you see here, they are sometimes they are closer to the equator. You have more activities closer to the equator. Sometimes it's away from the equator. You have some trends like this that are not completely understood. So yeah, you have all those sorts of, let's say, non-stationarity in the data, and some of them we don't know. So we try to do our best in terms of the pre-processing. Julia?
Could you go back to the data estimation part?
So it's one word, but behind it there are many different techniques. One of them is, for example, you have a sparse observation. So imagine you have a measurement, you have a physical system, and you have a measurement that just moves in this physical system, but it's a point measurement. For example, the temperature in the, I mean, I'm not an expert in weather forecasting, but the temperature in the Atlantic, you have a balloon that measures it, and you'd like to reconstruct a uniform grid of it over the time that your measurement went through this. So you run an inverse problem, and you have many techniques to do that to be able to recover basically more data based on the sparse observations that you have. It's a it's a way of completing it's a way of obtaining a more complete, a less incomplete state of your system. Of course. And what's important also, because we are not anywhere, we are at the Flatiron Institute, and we have many experts in the physical phenomenon that you're going to see in different applications. Go talk to them. When you're working on an observational problem, you have experts in magnetohydrodynamics at the Flatiron. You have experts in many different types of simulations. And also on different projects, if you want to generate your own physical phenomenon because you want your model to be more sensitive to this aspect of the physics, you have people that are the experts in their fields of generating this phenomenon for you. And just to give you an example, this is a project that Ruben led. Ruben was a postdoc at CCM. He's now at NVIDIA. With Mike, who's currently at Polymathic, in order to assemble a data set of fluid dynamics simulations, or more broadly PD simulations for machine learning. And we could not have done that if we were not at the Flatiron Institute. We have a lot of experts. Some of them are at CCM that helped us with designing this data. So being at the Flatiron Institute is very important. OK. So second point, training objective. And I separated voluntarily training objective from architecture, because I didn't want to show directly this is a transformer, this is a diffusion model, because what matters in the end is how you use them, how you use the architecture. I'll come back on this point. So you have different training objectives in machine learning: regression, detection, clustering, source separation, data assimilation is now more and more done with data-driven models. And these two at the bottom, next step prediction and denoising, that are more and more used for training large-scale models. And actually, if you take some of the tasks, for example, data assimilation, can be reframed in terms of denoising. I mean, it's not direct, but I could mention it. So I'm going to focus on these two, and I'm going to focus on these two in the context of our problem. So basically, we have a dynamical system, x of t. We're going to assume that it's uniformly sampled in time-space to make things simpler. If you want to have more insights on how to do data-driven models on graphs, for example, or other types of unstructured data, you have the talk from Teresa this afternoon. Where is Teresa? Hey, Teresa. Here, you assume that you have C channels in your data, C observations. In our case, I mean, it's not so important, but in our case, we're going to have actually 7 ultraviolet measurements, 7 extreme ultraviolet, 2 UV measurements, 3 magnetic field measurements. You have this co-aligned data. That's your input channels. And H and W, because you have images, it's the height and the width. The goal in that case, and it's the goal in general when you do prediction, is to build a model of the conditional distribution of the next state and the next states given the past observations. So that's it's not a scientific goal because it's too generic, but that's the problem that we wanted to tackle. That's the end goal. That's the things we wanted to deliver on the solar project. We're going to build a model, a predictive model of the solar dynamics. So that doesn't give you a way of training your model, and there are at least 2 ways that you can train your model. The first one that I'm sure you know is about next step prediction. And it's going to be deterministic. You have a network f of theta that takes, in that case, as input the 2 previous observations, and you train it to output the next prediction, the next observation. Why? So here you take two observations in the past. It's what GenCast is doing. Actually, GenCast is a diffusion model, so that would be more what GraphCast is doing for weather prediction. And here the theta, the f theta, of course, is the backbone. It's going to be the neural network in itself, and I'm going to talk about it in the next slides. Here I'm really talking about the training objective. It's separated. And I forgot what I wanted to say. So I'm not going to mention what is the backbone now, but there are people in the literature that trained a model like this with this objective. On the left, I show you an observed.
Hello?
Sorry. Yes.
Can you go back? So, can you scroll so that we get, yeah. So why is it only 2 time steps in the past? Or it's like just some history, some chunk of history? That's the...
It's in order for the formula to fit in the slide. It could be more.
Well, you have your reasons, cool.
I didn't put 1 because I wanted the possibility to have a model that does in-context learning, even if I'm not going to mention about it. If you only have 1, you don't necessarily know what the dynamics is. So you need at least 2 to have at least the smallest estimate of what the dynamics is. Yeah. If you have questions, don't hesitate to speak out. This is an observations. And this is a generation on the right of a model that was trained a few months ago by people at IBM and NASA with this training objective, next step prediction. So there is definitely smoothing. The structures that you see, they are disappearing very fast. I'm going to...
Sorry, I have a question there.
Please.
By generated, do you mean you're rerunning the predictor using its own output in order to simulate the dynamics way further into the future than you actually that used to set up the objective?
Absolutely. What I showed you would be...
So in a sense, it's not a surprise that it doesn't work for that, because you never trained it to work 40 time steps into the future. You trained it to work 1 time step into the future. Is that right? I'm
going to show you another model that was trained also with actually not 1 step, but 3 steps in the future, but that can predict up to hundreds of hours. So what I'm going to argue here is that it's not the fact that you are short range in the future. You could have done the same thing by predicting at the same time, let's say 3 or 4, even at further horizons in the future. You would have the same problem, and I'm going to mention why. Just in the next slide, but that's a good question. So as Alex is asking, where is the problem? Like, is it the training objective? Is it the model? The model is not well trained. Is it the training objective is not going further enough in the future? And actually, the problem is the training objective. And we can see it when we derive what would be the best minimizer of this loss. If I take an expectation on my data set, the best minimizer is actually the conditional expectation of future states given the past states. So you have an expectation. The expectation is taken under here the conditional distribution of your underlying process. So if this conditional distribution is wide enough, you take an expectation, you're going to average out all the different scenarios. So even if you have the best predictor, if your distribution is wide enough, you average it. And when you average, you're going to remove the structure that you have spatially. Yes?
But why is the distribution wide enough?
Very good question.
Is it because of the projection you're doing?
No, it's because of what I mentioned previously. Is because of the fact that you don't observe the state, the system entirely. I'm going to mention it right now, and then you tell me if it didn't answer your question. We are in a case, and it's the case in many, many different scientific problems, where the data you have is very incomplete, is quite not enough to characterize the system in itself. So imagine the sun. In the end, it's ruled by a PDE. If you had enough data and enough compute, maybe in 200 years, you could run a PDE solver, and you would have a unique solution of your solver in the future. Well, that's fine. But here, we observe only the surface and only certain measurements in the surface. So what you're observing is not enough to constrain the future of the observations in only one scenario. If you take, for example, like in the sun, you have things that emerge from the center of the sun to the surface. And now you don't see it emerging yet, and you want to predict the future. Well, you have at least two scenarios. One scenario where there is something that is emerging, but you don't see it. And one scenario where you don't see something because there is nothing. It's another scenario. So this is a case where the partial observability is really making this conditional distribution quite wide. Again, it's the distribution of the observations, not the states themselves. The states, you don't always have access to the full state. Does it answer your question? Does it answer other people's questions?
Well, it sort of leads, there's this big question of like, why would you expect that taking a 2D measurement is going to have any ability to predict what's happening when it's driven by a 3D, unobserved PDE? I mean, there must have been some belief that something was possible. That it's not just a random number generator. That the sun isn't a random number generator. In which case, putting the average out is probably the best prediction you're going to get. So.
It's a very good point. It's because we are not just interested in an emulator of the dynamics. I mean, that's the first answer to your question. But we could also be interested in, I have the atmosphere, I have the surface of the sun. I don't always have access to the surface of the sun because it's more complicated to observe. Can I have a model that reconstructs the surface from the atmosphere and suddenly completely these missions that are very costly? That question is way easier, and we can tackle it. I mean, that's new from 2 weeks. We actually have a very good model to do it, and the experts, I mean, they didn't believe us. So this task, I think you're just saying that this task is very complicated, but it's generic enough so that we can do a lot of things around it. Yes?
Is the point that instead of like averaging a distribution, we want to be like sampling from a distribution?
Exactly.
That is the distinction. Okay.
Thank you very much. So it's the training objective number 2. How do we sample from a distribution like in a deep learning setting, like in a training objective? What is the training objective behind being able to sampling? Well, these days, and it works quite well, it's to do denoising. And I'm going to mention why. So denoising, what you're doing in that case, so it's not a generic denoiser that I present here, it's a conditional denoiser. So you have a d theta, that is now your backbone architecture. Theta is your parameters. You give it the past as a conditioning, xt minus 1 xt, just like here. You give it also the data in the future that you have noised, and you ask the model to denoise it. So to output from the noisy data, the clean data. I realize that it's an intriguing remark, but if you take here the noise level to being maximum, you basically have something that is close to training objective number 1, but it's not so important. Here you have a variety of noise levels, and you're going to train your model to denoise your data. So this is what you do. This is what you do at training here. You have here clean observations in the past. You give that as information to your model to be able to better denoise the future. You have a noisy version of the future. You ask your model to denoise it. So again, it's not a research presentation, so what I'm saying is a bit hand-wavy. Here, when you ask your model to denoise the future and you give it the past, you start to make your model understand that there is a time dynamics that the model could use to better denoise the future. So that's the conditional part in conditional models. So why did we do denoising? Well, it's something that has been evidenced a few years ago. It has a direct link with generative modeling. And this is something that people have evidenced, people from Stanford, but also people from CCN that have evidenced it around the same time. Basically, when you have a well-trained denoiser, you can access what's called the score of the distribution of interest. The score is the gradient in space of the log probability. you have a direct link. It's a simple formula. It's a beautiful formula between what the network you train and this, let's say, quantity related to the distribution you want to model. Yes, Julia.
Denoising for generative modeling when you take like images.
Yeah.
Just wanted to generate images. Okay, but now you want to predict something scientific, right? It has to be true. So you do have different possible states.
What do you mean by, yeah, sorry.
Yeah.
Can you use your seat mic, please?
Oh, yeah, it's you need to push the button.
Better? Okay. So basically what I'm saying is denoising for this kind of forecast problem, you really want to be accurate in your scientific predictions, right? And you do have a probabilistic prediction. And like you said before, I mean, it's just one possible state that you're going to predict. So
Yeah.
Is there like a big variance on different possible states, or how do you handle that?
Yeah, so the way we handle it is going to be experimental. So with these type of models, we know we have theoretical guarantees that if we had enough data, they would model the distribution perfectly. Of course, it's in practice, it's never what happens, but we have these guarantees. But the main guarantee we're going to have is just post-training evaluation. Because it's not, I mean, it's a current area of research to add what we know of the physics in these types of models. It's like really a hot topic, and that's something we thought about it, but it's so much work to have some guarantees at training time that we don't have anything concrete yet. So mostly post-training evaluation, if it answers your question. Once you have the score, you actually have a sampling algorithm that is based on discretizing these backward stochastic differential equations. And what happens is you start from noise in the future. Then you call your diffusion model to ask it to remove a bit of noise, then to remove a bit of noise, et cetera, until you're at a completely clean data point. But you don't have information in the future. So here you really start from a pure white noise. And that's what you generate. And every time you restart the process with a different white noise, actually even with the same white noise, since this one is the SD, you're going to obtain a new generation. So that's a way of sampling conditional distribution prior when you have trained a denoiser. So the training objective is denoising. Then at inference, you have a way of sampling a distribution. And this is the second training objective. Again, on the left, this is your observation. So you see it's shifting a bit. It's because this video, I did a mistake. I didn't reproject it. So the prediction on the right is not going to be shifted. And this is what your model gives. So there is no more, visible smoothing. You're capable of rolling your model in the future for many steps. Here, maybe I should have mentioned it. This is what I mentioned it a bit briefly. Every time you predict something, then you just move your model to take as input what you predicted as a new conditioning to generate the next step. Then you do this with the next step, the next step, the next step. So it's called rolling out a model. So all this is just visual, but visually, we were not expecting to have a stability up to several hours, and basically we have stability up to the rotation of the sun. What we see, if we take an image at the left of the sun, and we are capable of rolling it out all the way to the right of the sun. So these models, they are used more and more, in particular because they are more stable. And again, here you predict a scenario. You could predict another scenario. You have now a model that is intrinsically a generative model.
Ask again an ignorant question. In essence, this is solving, by these techniques, some kind of differential equation that takes an initial condition and propagates it forward in time.
Yeah.
Okay. What are the conditions on the differential equation that you're trying to solve which would make this work? And are there kinds of differential equations for which it would fail?
Can I ask you, do you mean with this type of models, if we apply it, can we apply it to any variety of PDEs, for example?
In general, is there a connection between the kind of models that you would use in this context and the kind of PDEs you can solve?
Yeah. So technically, there is no. I mean, it's a tough question because I don't want. The answer would be we don't know. There is no link. The answer would be like we don't know yet if there are any PDE classes that are better modeled by diffusion models. What I think is important is again this point of observability. It's not necessarily, I think, the PD in itself, and I don't know how to answer your question, but I think that the most important thing is really, do you have access to the entire state of your PD or not? And I don't know if I'm pretty sure that the sun is a chaotic system, but I don't know. But if you mentioned chaotic systems, of course, if you lack some observations for these PDs in particular, you absolutely want to have a generative model and not a deterministic model. That's what I can say at this stage, but it's a hard question. Yes?
If you go back a slide. Sorry, one more. So what is the source of the noise in the two images that are then cleaned, and like how are they cleaned? Just it seems kind of abstract. Like what are you doing to the first two images?
Yeah, that's a good point. I didn't mention it. So here x is going to xt plus 1 is your. I'm going to repeat your question. Your question was, what is the source of the noise in these two images? Because it's a bit algebraic here. What we do is we have this xt plus 1, which is an observation in the future. And the epsilon here is a pure white noise. And sigma is the strength of your noise. It's going to be the scale of your noise. And basically, you want to have a sigma. You're going to have a sigma in your training set that is going to be from almost nothing, 0.01, for example, in terms of if you have normalized data, to something is around 100, so where your data is going to be completely noisy. And here you start with the same distribution, a white noise, Gaussian white noise. Does it answer your question?
I mean, is that term the difference between what you would have predicted for t plus 1 from t versus what it actually is?
Here, are you talking about this term?
On the left.
On the left. So here, this d theta is going to be predicting, so in this example, it's predicting an image. It's supposed to be a clean image. And you compare it to the clean future image. So if your model is well trained, it should predict something close to the clean image. So what you take as input is an image, and you output an image.
So it's sort of like quantifying the wrongness of the prediction of t plus 1.
Yes, exactly.
Okay.
Exactly. Yeah.
And that's the noise. Yeah. Okay. Thanks.
Absolutely. Yes.
You've mentioned partial observability a couple of times, and I was wondering if there's anything that prevents you computationally from including further time points in the past, because typically if you observe one variable in a multidimensional system, you can kind of supplement learn something by embedding further and further in the past, something like up to the time scale of the lifetime of the structures you're interested in.
Absolutely. So ideally, we would take the measurements that are as far in the past. If, in particular, with these processes, you have beautiful power laws in terms of the decrease of the correlation. So you're like, I want to go further in the past. And that's actually what we do. I didn't want to add any complexity to the problem, but we have a multi-scale scheme that takes refined measurements close to the present and is less and less refined to be able to go further away in the past with the same compute budget. In the end, it's going to be a question of compute budget, and we take 4 times as conditioning. All right, so moving on. These are very good questions. We have a training objective, it works better than a deterministic objective. Now we're going to talk about what is the architecture. Who heard of what a transformer is? Raise your hand. Yeah. 60%, 70%. Who actually trained the transformer themselves? It's why I say, I say that because I fear that all the questions you're going to have are just going to be answered by, I can't really answer easily, you should look at the code. It's really a bitter lesson that I've been through myself because I was doing more applied math and before that a bit less applied math. But in the end, the things are happening in the code, and that's annoying. So transformers, 3 of the applications that I mentioned are actually built on a large transformer. What's a transformer architecture? I'm going to try to describe it as efficiently as possible. So it's a neural network, so it's a sequence of nonlinear and linear layers, and you basically have 3 types. So here you go from your data. Here it's called latent, but you should forget about latent. You have your data here, and then the first step is to be able to encode it. So typically you have data that is of shape T. It's the number of times that you have. HW is the size of your image. And C is going to be the number of measurements, the number of input channels that you have, magnetic field, light, etc. You patchify your data because you can't process with a reasonable amount of memory entire images. And you get a sequence of patches. Each patches has different measurements. So this is why here I say that the transformer is processing a sequential data X of shape N. N is your number of patches. It's also called tokens for us. And D is going to be the dimension of each patch is going to be represented by a vector. So you go from your measurements to a higher dimensional vector through a linear layer. So I'm not talking so much about encoding and decoding, but it's really, I think it's quite a subject in science, but in any scientific applications, because we know we have access to good encoders for text, for images, in computer vision. For the type of scientific data that we tackle, we almost never have the encoders. So this is more of a default approach rather than an ideal approach. There would be a lot of discuss here. Second type of layer, attention layers. So attention layers, it's basically doing a product on your data. So if you have a sequence of tokens, of n tokens, each of dimension d, you're going to basically take your tokens, multiply them by themselves with a certain transformation WQ, WK that adds learnable parameters to be able to change the way you do the product, basically. You do your product here, you get a matrix that is of size the number of tokens times the number of tokens. And then you apply it back, after a softmax, of course, to your tokens. So you have something that takes your tokens, multiply them with themselves, apply it to the tokens with some learnable parameters everywhere. And so it takes a sequence as input, and it outputs a sequence. That's what attention is. Feed-forward layers are important. Every time after every attention block. So here you have a attention block, and you're going to have many of them. For the Solver model, we have something like 24 or 36, depending on the model size. And each of these blocks, you have an attention and a feed-forward network. Feed-forward network is just going to be operations in the token space, so along D. Linear operation, nonlinearity, linear operation. Funny enough, in the current architectures, most of the time, the time spent training your model is on the feed-forward layers, not in the attention. So it's called yeah. So what are the key aspects? You have a sequence-to-sequence model. It takes sequence of tokens and output sequence of tokens. It's highly parallelizable. That's when it was released. That was really the new thing. Instead of doing something autoregressive on your sequence, you can process everything at the same time, and in particular, you can go parallelize it. So that's why also these attention layers are not the bottleneck, because they were made quite faster for reasonable length of reasonable number of tokens. The feed-forwards also, they're going to be applied token per token, so they can be parallelized. In the end, you still have this problem that this is quadratic in the length, in the number of tokens that you have. So if you want to, you're not going to be able to process millions of patches easily. In particular, you have people, I'm not going to mention it, but you have acceleration on that. You have a whole subject that is how to apply these methods to long contexts. It's going to be important for us if you want to have patches that are very small. It increases the number of tokens you have. And having patches that are very small is nice because you're able to better model the fine scales typically. That's basically how it works. So why am I talking about transformers? It's because they are fast and scalable. I mean, I would like to say that they are a principled way of tackling this type of data. I don't know. They are fast to train, and they are scalable in the terms that when you increase the model size, the performances really improve. Yes?
When you're working like in a patch-by-patch way on these images, I worry that you might have like artifacts at the edge of the patches.
Yeah.
Does the field have good ideas about how to handle that?
Yeah, so there are methods to handle that. In general, when the model is, it's empirical what I'm going to say, but in general, when the model is correctly trained, you don't have these artifacts so much. Also because in the denoising process, you're going to noise your observations and denoise them. So it's any error you make, maybe a bit improve that inference time. But you also have methods that shift the window to make sure that the artifacts you make, they are not always at the same place. All that is going to be signal processing techniques, and you have a lot of research on that. But it's a good point. OK, so that's the architecture we chose. An important point is the training. And I think I only have 5 minutes remaining, something like that.
Since you took questions, you can take the time.
Yeah. I'm going to try to give you some training principles. Again, it's not a research presentation. Please, if you want to raise a principle that I forgot, don't hesitate. Principle 1, when you train a model, you should maximize memory. It's a bit weird at first, but why it's the case? It's because scaling laws have shown in most of the cases that for a fixed compute, if you have a larger model, you're more efficient at training it. It's a bit weird, efficient in terms of the loss. So here, if you take this curve, you have on the x-axis, you have the training compute. On the y-axis, you have the performance. The smaller, the better. Here, imagine I have a fixed budget of compute. The smaller model is doing not as good as the small XL model, not as good as the XL model. And that's actually something we saw. We recently just, with the same compute, run a larger model. And in a few days, it has the same performances as a model that was trained for 1 or 2 weeks. So it doesn't mean that you should use all the compute like in the world. It just means that if you have a fixed amount of compute, use all the memory because it's going to enable you to scale your model and be more efficient when you train your model. Principles number 2, this one is very important. Use a standard training script. Don't code your training script yourself. It's a mistake. We are in 2025. There are people everywhere, including in the Flatiron Institute, that coded their own training scripts. They are very good. They are perfect. Use them. The main thing you're going to see is that the training scripts you use, the data loading process is not going to be very good. So the way you assemble the data and feed it to your model is because, in general, the training scripts, they are for text. And text is going to be gigabytes, maybe terabytes. I don't know. In our case, it's petabytes of data. So it's going to be the main part that you're going to have to work on. Optimize data loading, I mentioned it. Monitor training, OK. Scale and regularize data with model size. So if you increase the model size on the same small data set, you can't expect to get better performances. You need to also increase the data you have. A way to increase the data you have is to do some regularization. And in particular, just a point on diffusion models. This way of noising the data with every time a new noise, denoising it, it's in a certain sense a way of doing data augmentation because your model is not going to see only one data every time. It's going to see all the noised version of it. And so that's why also people use these models, is because they continue training even in the end of the training. That's one explanation why these scaling laws are continuing for these models. sorry it was not so clear. OK. Last step, evaluation. I'm not going to mention so much about it because that's the part that's going to depend mostly on the type of scientific task that you tackle. In that case, so this is the same video that I showed generated from our model. We generate also magnetic field with this model. This is a video of a magnetic field, the radial component. And you can generate many realizations at the same time. Again, it's a form of summary. We have a model that is a diffusion model, so you can generate different samples. Visual, of course, visual. So what can we say that is a bit generic? Visual evaluation is going to work at the beginning. You just want to make sure that your model is not completely wrong. The goal is to have a generation that is indistinguishable from a data in the data set. So you show it to the experts. You show 2 generations. They tell you, this one was your model, this one is observed. If they are true 50% of the time, you won on the visual evaluation. At the moment, we are at 70% because the experts are very good. Of course, one of the things that I think is a bit generic is that you should use summary statistics. In general, it's a lot of domain expertise that is involved in general in building these summary statistics that basically characterize your data and what you should retrieve in your data. In that case, we have these summary statistics, and we just make sure that they are preserved in our generations with the time. These summary statistics, they're really beautiful. It's something that the solar physicists have explored for years, and is going to be change in the polarity or measuring the polarity on certain pixels. This is really a work that you can't really do yourself if you're not an expert in the field. So again, it's very important to rely on domain expertise, people at the Flatiron, people around, people nearby. All right, so there are many things I didn't talk about. It's already the end. Something very important is latent diffusion models. How can you basically compress your data further and do probabilistic modeling in the compressed space? That one is very important. It's not possible all the time. We could discuss it. Very important, multimodal models. I didn't mention it, but you have more and more architectures that basically scale and completely try to consider the universal tokens. Instead of building tokens for your data, you're going to have tokens from your data set. You're going to have tokens from another data set that you align. In the end, you have tokens, and you have these architectures that are transformers that just process tokens. So people have pushed the boundaries of what you can do with tokens, and this is multimodal models. Low-rank fine-tuning, post-training methods are very important, and they are completely underexplored in science. Reinforcement learning, post-training methods. Once you have a model trained, how can you improve it without changing the weights, without having to redo a training? And it's something that we are working on at the moment. I can give you a very naive example. You have a model that can generate many different samples, and now you want to have access to the samples where the polarity is completely neutral. Well, you just have your model generate many samples, and you remove the ones where the polarity is not neutral. It's very naive, but by doing so, you get a model that is better in a certain direction. And in essence, that's what the other techniques are going to be about, the more complex techniques. And I think on that, I'm finished. Thank you.
So we have a couple more minutes for questions. Please use your seat microphone when you ask a question.
Yes.
You mentioned the summary statistics at the end. Do you not/never use them during training?
Yeah, it's a question we had, and it seems that the model reproduces them in the range that we expected. So we were planning on incorporating it in the model. We finally didn't do it because it seems that they are they are okay reproduced. Yeah, we had that in mind. Yes.
What happens if you take like this technique and use it like on a 3D OD? Like you take a Lorentz attractor that you know is chaotic, but it has like some type of periodic thingy. Like how well will it actually be able to reform the actual dynamics?
Can you precise the type of system that you mentioned? A 3D?
The 3D Lorentz attractor, the one that does like the...
That's a good question. I've seen papers doing it, but I'm not sure. I don't know, but I don't see any fundamental problem for this model to not be able to approximate the distribution. Now, to give you some exact prediction, I think it's not possible. To approximate the distribution, I don't see why it would be so hard. Any other questions? Yes?
Did you experiment with different architectures or anything like that? I mean, I had a problem like this with an undergrad some years ago where we used a conditional generative adversarial network to make predictions of the near side solar surface from 7 days in advance from far side magnetograms. And it worked very well and was very efficient and things like that. It seems like this could be very expensive. Did you explore some different architectures or things like that?
Yeah, so it's, we didn't explore GANs, for example, because we think in that case it would have been quite hard to train on the amount of data that we have. It's true that diffusion models are going to be more expensive, so they are way better, but it's at the price of being more expensive in terms of cost, absolutely. We experimented variations around the denoiser backbones, so changing the way, so for example, the new thing is to do some MLP residual stream that's from the Llama model. That's something that we tried on in our case. It worked way better. We did these small architectural changes, but not like fundamental training objective changes. And I think, like at this scale, I think it would be quite hard to train a GAN. But I mean, I can't prove it to you, unfortunately. Yes.
2 questions. First, why tokenize if you have numeric data to begin with?
Because it makes your model work simpler. Imagine you tokenize your data in a discrete space, then you're suddenly working with discrete tokens and not with numerical ones. You can now go in a way lower precision. You save a ton of memory. You can train larger. You have a better model. That's one example, but there are many. To answer your first question.
Okay. Second question, you presented the 2 objective functions, and I thought it was very interesting, the different kinds of predictions that you get. It also seems like they may be related in the sense that the blurrier the predictions from expectation, you should also get more variable predictions from the diffusion objective. Have you looked into something like that before?
Yeah, it's true. It's true, and so and you have a continuous trade-off. It's something that is called dispersion or distortion trade-off. I'm always confused about it, but it's people have identified in computer vision that you have a trade-off, and you can measure where you are in the trade-off with your model. You can have a loss that is between reconstructing the distribution and between reconstructing an exact scenario in the future. You have a whole bunch of literature in that. We didn't do the study because I think it's already there. But it's a good point. Thanks. Yes.
Kind of relates to the question I had, like also I asked before. Like, do you have a sense of how variable your predictions are? Like, is there like, are they close together or very dispersed or?
Yeah, so we definitely track the standard deviation per pixel. So we have the different scenarios, and we check per pixel how the pixel is going to vary across these different scenarios. It changes a lot in the, like, I think what we observed is that the main variation is really in where you start your model. If you start it at a very active region, you're going to have a lot of variance. But I mean, we don't have precise, because in the end, we don't just want to say, we observe that on this type of visual images, we have this type of variations in the model. We want to give a message to the heliophysicist. That takes a lot of time. So we
exactly. I think it's more important to look at the, or at least, I think for me it's more interesting, is the variability, like scientifically speaking, right?
Yeah.
Not necessarily the visual part, but like the scientific impact of the forecast.
Absolutely, and it's something you won't be able to answer completely. There is one thing that we observed, and that's validated, is that you have some regions sometimes on the magnetic field that are going from negative to positive, and it's non-physical, but it's in the data. It's because the way the data was assembled, you have sometimes a +1 and a -1. There is an ambiguity. In certain cases, we saw that our model is also having this ambiguity. Like you see that there is a small dot that is actually pointing upward the surface, but it may be wrong in itself in the data, and the model sometimes put it positive, sometimes put it negative. So there are some uncertainties that are captured by the model. To have a complete answer to this question is going to be a lot of work. Thank you.
Let's thank our speaker again.